So I didn't show you where this ellipse equation came from, and there's a reason. It's a really long derivation. It takes a long time to find it. The parabola I can show you in like a minute. This one takes a while. So I still want to show it to you, but just realize that you probably won't ever have to do this. But I think it's important because it's not just magic. It feels kind of magical how easy the equation turns out to be. But let me show you where it comes from. So we're going to start with an ellipse. Beautiful ellipse. And these are the key things we know about it. Another key thing that we know is that if you were to connect the lines to one spot from the two different foci, you're going to get the same distance when you add them together. Now, I tried to have you picture like attaching a string at the two C's and then putting your finger stretching out the string, and if you trace out letting the strings guide you, that would be an ellipse. We actually even know how long the string is because the distance from this focus all the way over and back would be, well, it would be the whole length of the semi-major axis except for this little part is being doubled, but that happens to be the same over here. So what I'm getting at is the string, when you add this up, the string does not change. It's always a length of the semi-major axis. So we're going to find the distance from there to there. We're going to add that to the distance from there to there, and then it's going to be equal to 2a. And using that, we can figure out the equation that we were just using. Okay, so hang on. This is going to be a long ride. So first of all, the distance from here to there is going to be, well, you do x minus c, so that's going to be x plus c squared. Y minus 0 is just y squared. We're going to add on the other distance between the other focus and that point, so that's going to be square root of x minus c squared plus, again, it's just going to be y squared because y minus 0 is y. And this should all equal 2a. All right, now what I'm going to do, and this just comes from experience, I'm actually going to subtract this term here over to the other side because what I want to do next is square. I want to square both sides. And it actually is a little nicer this way. Just trust me here. Now if I square the left side, I'm going to get this right here, which is x plus c squared plus y squared. It just undoes the square. On the right side, I'm going to take this whole thing and square it, which means I'm foiling. So this times this is 4a squared. This times that, and that times that is going to be the same thing. So we're going to have 2 times 2a negative this. So that's negative 4a square root of this stuff. And then lastly at the end, this squared is going to be positive x minus c squared plus y squared. Okay. So far so good. What I'm going to do now is actually expand the parentheses. So this parenthesis x plus c squared, I'm going to write out as x squared plus 2cx plus c squared plus y squared. And then I'm going to do the same thing on the right side. So we're going to have 4a squared minus 4a square root. And I'll just leave this stuff under here for now. But this is going to be x squared minus 2cx plus c squared plus y squared. Okay. So now that we've foiled all that out, I'm going to look now because I've noticed that there are terms on both sides that are the same. So what can we cancel out here? We can cancel this with that. C squareds. We can cancel y squareds. And what I'm going to do is add this 2cx over to the other side. So I have 4cx is 4a squared minus 4a square root of x minus c squared plus y squared. Okay, so that got a little bit nicer, but it's still not close to our ellipse equation. One thing I do notice is that there are 4's all the way across, so we can cancel out these 4's. Just divide everything by 4. And the next thing we're going to have to do, we're going to have to square both sides again to get rid of that square root. So before I do that, I'm actually going to swap things around. So I moved the square root to the other side. I subtracted cx over. Now when I square it, it's going to be a lot easier to work with. So here we go. This is going to be a squared times the stuff inside. And then we have to square this too. So that's going to be a squared and a squared is a to the 4th. And then this times that is going to be minus 2a squared cx. And then this times itself is positive c squared x squared. All right, now the other thing we need to do on the left side is expand out this. So this would be x squared minus 2cx plus c squared plus y squared. Okay, so we're getting even closer. We still have to keep simplifying. So one thing we can do is drop the a squared in here. 2a squared cx plus a squared c squared plus a squared y squared equals, and to make things easier, you notice there's a lot of a squareds. I'm going to write a squared instead of a to the 4th, just in case. This is a squared cx plus c squared x squared. Okay, and then it may look kind of hopeless right now, but there is some magic going on here. We actually have the same term on both sides. Those ugly things are going to be canceling out. And we have a squared x squared. I'm going to get the x's together, so I'm going to subtract that over. All right, and then we have a squared y squared. And I'm going to get these that don't have an x or y together. So I'm going to have a squared, and I'm going to subtract a squared, c squared. Now, a really important part that's really hard to see if you don't know what to look for. This right here, they're like terms. And so what I'm going to do is factor out an x squared so that I have this right here. And same thing over here, I can factor out an a squared, and I have a squared minus c squared. Okay, so you might start to see the beginnings of the ellipse equation. There's just one last step here, and that is we have an expression for a squared minus c squared. We got to go all the way back to the very beginning here, and I'm going to erase these two strings. Remember that if we were to put the string right at the top here, this would be A, because that's half of the string. This would be B, and this would be C in a right triangle. So, B squared plus C squared equals A squared. And now, if you ever see A squared minus C squared, that is actually the same as B squared. So going back here, to the end of what we were doing, A squared minus C squared is the same as B squared. Okay, holy cow, that was a lot of algebra, and we're just one step away. What we're going to do is divide everything here by a squared b squared. Now what does that do? Well, b squared all over a squared b squared, the b squareds are going to cancel, and you have x squared all over a squared. If you do a squared over a squared b squared, the a squareds cancel, and you have b squared. And then if you do this over that, it's just going to be a 1. So there we go. That is why the equation has its form. Now, originally when the Greeks were dealing with ellipses, parabolas, and so on, they didn't deal with it this way. They were using constructions. They were using physical ways to create these perfect shapes. It wasn't until Descartes and the Cartesian graphing system when Descartes started assigning points with coordinates x, y, and he was the person that kind of wrapped this all up and put them as equations like this. So there you have it. Again, you won't have to probably ever do that, but I think it's important to see that this isn't magic. This is just really cool.